Make sure you realize you can check your answers with your calculator. Again, checking it a second way helps you have some confidence in what you're doing. If you take your model function for part A here, if you want to know how much is after 24 hours, think about how many times it's divided. 850, 2 to the power of 24 divided by 5. That exponent, it's not quite 25 hours. If it was 25 hours, you wouldn't really need a model function. You could just keep going with the table, right? Because you can just keep doubling it 5 times. It hasn't doubled 5 times, it's doubled 4.8 times. If you plug that in, what do you get? What did we get for an answer here? 975. Almost another bacteria. What should we do here? There's always an argument for whether, now should we round it up? Like, once you, if it hasn't got to that next one, you don't have one. But for the purposes of math, I would say don't put decimal point for bacteria, but I don't care if you round it up or down because you can make an argument either way. If you're doing the provincial exam, they would want you to make this, like they would want you to mathematically make it that, right? Realistically, this is too accurate. If you're really doing this calculation, in real life, you're just modeling a real situation. It's not actually going to be that many. It doesn't behave exactly like this function. This is a good approximation, but as a math question, round it off to the closest number. But in reality, if you said it'd be about 23,000 something or other, that's about as good as you're going to get. The other part's the more difficult part, I suppose, because here up here you are finding y. You don't need logarithms for that. Here you're going to be finding x. We want to know, when is this going to be 1 million? Okay, 850. Seems like a big number, but again, exponential growth, it goes pretty quick here. If you want to solve for that, there's no difference just because that 5 is there. Just deal with that at the end. I would say the simplest way is to divide this first. Don't multiply the 850 and the 2. X over 5. Take the logarithm of both sides. If you want to reduce this first, you can. I'm just going to leave it like that and deal with it at the end. I have log of this. I guess I could take off a 0 if I wanted, but I'll leave it like this. You're going to have log of 2 to the x over 5, and just like before, that can go in front, right? That goes over there. So you got x divided by 5 times that. And then just like anything else, if you're trying to isolate this, you're trying to isolate that x, multiply both sides by 5. Right? So I got 5 times what's on this side. And that gets rid of the 5, and then divide by log 2. And that gets rid of this, right? Divide this side by log 2, and times it by 5, that'll get rid of both of those things. If you put that in your calculator, it'll give you an approximate answer here for what x is. What did you guys get? 51.001. So I guess if you're asked to do it, I don't know if I said to 2 decimals. If you're giving that to 2 decimals, what do you say? Yeah, except if you say it's 51, you're saying that, like if I say x is approximately 51, it sounds like all I did is to the nearest whole number. Unless it's exactly 51, in which case you would do this. But if you're rounding it off, if I say x is approximately 51, if I want to say I went to 2 decimals and it was still zeros, put those zeros down there because you're saying it's 51 accurate to 2 decimal places. There's a difference between saying that and saying that. It's talking about how accurate you went. Anyways, if you want to check that on a calculator or on some kind of graphing software or whatever, I'll use a calculator first. If you want to do this, you need to graph that model function and set up your window. So what was it here? 850 times 2 to the power of... Now you need brackets around this exponent here, x divided by 5, because it does order of operations. If you don't put brackets around the exponent, it's going to not graph it properly. We said well, we already know the answer is 51, so I'll make x go up to 94. just because of the number of pixels there. We'll go 10 at a time. And we know we're looking for it to be up at 1 million before that, so maybe we'll go 2 million. Probably not enough. It'll probably go off the screen before we get to the end. 100,000 is a good scale for that. Not that it matters if you're just checking, as long as you can see it. Okay, exponential growth. It looks like nothing's happening here, and then it goes off the top of the screen here. The way you need to do it on here, because it's easy to get it to calculate a y value for an x value. So I could do this. I could say I'm going to put in 51. Look, it's approximately right. So probably I'm right. Incidentally, if you want to see the whole graph, these numbers cover it up. What you could do is instead just make this a negative number here. Negative 400,000 or something. Because then there creates a space at the bottom. You could do what I just did there. If you're checking an answer, you could just put in a number. Or you could trace and just have a look here. I set up my scale so I can go to pretty close to 51. If you aren't sure though, or if you want to do it exactly, what you can do is you have to put in a second equation if you want to work backwards here. And graph that and just find the intersection of those two. So that's where it's going to be number 5 here. And you first curve, second curve, guess. So there's that number, right? 51 point, that number you told me before. Okay, hopefully you are able to do that. Grab this. I'm going to mess that up. Let's look quickly at the question after it on radioactive decay. Our basic setup now, before we had kind of a times r to the power of t or n or whatever you're using there, this is if you would think of it as the period is 1. Like the rate is being applied every 1 unit of time. If we have the rate being applied in a different period, we have to adjust this. And we're going to adjust it as t divided by, I'm going to use the letter p for period here, like we did in that previous question. Not 1. Okay, e.g., it's doubling every 5 years, like that question, right? The period is something different. Here, the period is 1, it means like 3% per year or tripling every year. Month, whatever the unit of time is. If the rate is being applied every 1 unit of time, you don't need to bother putting that thing underneath there. You could, it's just going to say 1, and that won't change anything. But just realize that there's those two, not different, but related situations that we have to deal with here. Which of those things require logarithms and some sophisticated grade 12 math to solve for? And which of them are easier to solve for? Those variables. Because there's 5 variables in this one you could be asked to solve for, but not all of them require grade 12 logarithms to solve algebraically. When you were asked to find this, did you need logarithms? Not really, you just need a calculator, right? We solve for the time. Do you need logarithms for that? What's the other thing you think you need logarithms to solve for? We haven't done it yet, but yeah, this, right? You could be asked to solve for this. So there's a question in here that asks you that. Okay, down here. I think I put one in here. Maybe I didn't. I did on the next problem though, right? What's the half-life of the substance? Not sure how familiar you are with radioactive decay. I'm sort of assuming you're somewhat familiar from some of your science courses. But you can set it up the same way. Half-life, there's a description here.
You're also 10.
Oh yeah, thanks. Half-life is talking about if the half-life of something is 28.1 years, in that period, half of the material decays. So I'm thinking that should be enough to have you set this up here. 28.1, half the material decays. Can you try and set up a function for that?